All right, so does everyone see the material on Canvas?
Yes.
So the syllabus, the lecture in the YouTube video, and the homework? Okay. So I'll post the answers to the homework, I think, tonight. Maybe give you some more problems tonight. And so at the end of the week, I'll give you a full solution, step-by-step solution to the homework. But for now, try to work it out on your own, see if you get the answers. Are there any other questions on anything before I start? All right. So the last thing we were doing was talking about the dot product, right? So the dot product, just so you remember what we were doing, there's two ways to find the dot product. One way is using this equation here. It's pretty easy. It's just the magnitude of the two vectors multiplied together times the cosine of the angle between the vectors, right? That gives you this thing called the dot product. And so this is one way to find it. The other way to find the dot, use the dot product is this. AX times BX plus AY times BY. That's if you know the components of the vectors. You can use this equation to find the dot product as well. So there's two ways to find it, and depending on what you're given, determines which equation you use. So we're going to do a couple sort of simple examples of how to use it. It's really not that hard. So we don't have to go crazy on these examples, but just to show you how it works with a couple of examples, we'll do two examples here. All right, so I'm actually going to, all right. Okay, so examples, okay, so one, okay, vector A has a magnitude of 10 and is directed at 30 degrees counter clockwise from the positive x-axis. Vector B has a magnitude of 5 and is directed in the positive y direction. So it's completely in the positive y direction. All right, so this is pretty straightforward, hopefully. What is the dot product of these two vectors? It kind of helps to sketch out the picture. You don't have to do it if you can visualize in your head or if you know what you're doing, you don't have to do it. But it helps to sketch out the situation here. All right, so vector A is 30 degrees from the positive x-axis. Now, technically speaking, it should be twice as long as vector B because the magnitude of vector A is twice as big, but it doesn't really matter that much. All right, so this is vector A. It's not to scale or, this isn't 30 degrees exactly, but it's supposed to be 30 degrees. Okay, so that's 30 degrees, right? Where's vector B? So it's on the positive y-axis, right? So it's like this. It's like half as long. It doesn't matter if you get it perfect, but that's vector B. Okay. So what do we know here? We know the magnitude of both vectors, correct? And we know their angles. So there's two forms of the dot product. One is AB cosine theta. One is AX BX plus AY BY, right? So which one do you think is best to use for the situation? AB cosine theta or AX BX?
AB cosine theta.
Right, because we know the magnitudes and the angles, right? So this is the best one to use. So A dot B, which is what's known as the vector dot product, is that, right? Mm-hmm. And we know A and B. I mean, the magnitude of A and B is 10 and 5. But what is theta? So what should this theta be?
60.
Yeah, it's the angle between A and B. right? Less than 180. So the angle between A and B is 60, right? Because those two angles add up to 90, right? Because they're complementary. So you don't use 30, right? Or 90. You use 60, right? So you get and the cosine of 60 is a half. Sine of 30 is a half, cosine of 60 is 1/2. Positive 1/2. Remember, the dot product can be positive or negative, right? Just whatever the angle is. Sometimes the cosine of an angle is negative, right? We went over that. But here it's positive. So you get positive 25. That's the answer, right? That's it. That's the dot product of A and B. Does that make sense? All right. So let's do a slightly more complicated problem. All right, hold on. Okay, so okay, so suppose I'm going to handwrite it because it's hard to type, I should say. So suppose you have vector A, and it's given by this. I'll explain what this is in a minute. All right. So this is something I haven't seen before. It's negative 3t times x plus t times y. So t is some variable. It can be anything. It's variable, right? It can be 1, it can be 2, but we don't know what it is. That's going to be part of the problem. B all right, once again, t is something we don't know. It's part of the problem, right? But we know 2. So this we know, right? The x part of b is 2. That's something we definitely know. So the question is, what value, of t is needed such that these two vectors, it's actually maybe 2 values, but whatever. So it could be values, so value of values. Of t is needed such that these two vectors are perpendicular to one another. So d can be anything, right? So for one or maybe more than one value of t, these two vectors will be perpendicular to one another, 90 degrees away from one another. Does anyone have any idea how you would answer this question?
You would multiply negative 3t times 2, and that would give you the x hat portion of the dot product, and then multiply t times 5t, and that would give you the y component of the dot product.
Yeah, what you're saying is fine. So they're not really components, but I understand what you're saying. So first of all, we know the x and y parts of these things, right? So we're not going to use this form of the dot product, right? Because we're going to use the other one, right? Because we know the x, right? We know the components is what I'm trying to say. So we're going to use that in a second. But how do we know if two vectors are perpendicular? What's the angle between two vectors that are perpendicular? 90. Right, and the cosine of 90 is 0, so that means their dot product is 0, right? So what we want to do is take the dot product, see when it's equal to 0, and then solve for t, right? But the point is, what you're saying is right, so we want to use this. Okay, so let me just mention that. When a dot product is 0, vectors are perpendicular. So this would be a pretty hard thing to do if you didn't know about the dot product, right? I mean, you can do it geometrically, but it'd be kind of hard to do, right? So we're going to use this form of the dot product. Because we know the components, right? So this is what we're going to do. So it's 2 times minus 3t plus 5t times t, and we want this to be equal to 0, right? So that they're perpendicular. That's the whole point. So what you get is minus 6t plus 5t squared is equal to 0. So what you can do is you can factor this. So you factor t out, you get minus 6. So there are two solutions, right? So either t is equal to 0, because that's one solution, right? If t is equal to 0, that's the solution to that equation. Or the parentheses is equal to 0, right? So this is equal to 0. So if you solve this equation for t, what do you get? You get 6/5, right?
Yeah.
So those are the two solutions. If t is equal to 0, they're perpendicular. Well, actually, hold on a second. So no, this doesn't actually work. Let me tell you why it doesn't work. Okay, so if t is equal to 0, what do you get for a? You get 0, 0. So it's not a vector because both components are 0. So technically it doesn't work because t equals 0, a isn't defined. So that technically isn't the answer. Mathematically it's the answer, but physically speaking it's not an answer, right? So really the only answer is t is equal to 6/5, right? Okay. So if you plug in 6/5 for t, those two vectors, when you sketch them out, would be perpendicular, right? Okay. So does that make sense?
Mm-hmm. So we should always go back and check.
Yeah. Make sure one of the vectors isn't 0, or else it doesn't really work. All right. Okay, so does anyone have any questions with the dot product or vectors, what we did yesterday? No? Okay, so now what we're going to start to do is use,
Go back earlier when you started doing the dot products, the 2 times -3t, the first line.
Mm-hmm.
What's the formula for that? How do
Yeah.
you know it's like that? It's ax bx. Oh,
Yeah.
Thank you.
Yep. Okay, so now what we're going to do is we're going to start applying vectors to physics, right? That's the whole point of learning these vectors, so we can start applying them to start doing some physics. So the first thing we're going to do is start talking about kinematics, describing how things move in a sort of mathematical way, so we can analyze it, right? How things move. Okay, so this is the next bit of notes here. Yeah, I haven't posted these notes just yet, but I will post them. Oops, sorry. I will post them this afternoon. Okay, so suppose we're going to start with, it's a little bit weird, but it's easier to actually understand 2D kinematics before we understand 1D kinematics. It's a little bit strange, but we'll see how it works. So 2D kinematics is how things move in 2D, right? We're going to precisely describe how things move in 2 dimensions, right? So basically, if you're walking around this room, you walk in 2 dimensions, right? I mean, on the floor here, right? If you don't step up here. Else it's in 3 dimensions. And so as you walk around the room, you trace a path, right? If you painted your motion as you walk across the room, you see this path drawn behind you, right? Describing everywhere you were, right? So this is what this line is here. So suppose you're in a helicopter, right? You're looking down at someone walking across FAU, and they start here, and then they eventually move to here. This path here is the path that they trace, right? So this is what this is here. So the first thing you can do when you're trying to describe how things move in 2 dimensions is draw this vector here, which is called the displacement vector. This is the first sort of physics vector. It's called RT. I'll explain why there's a T there in a second, but let me just show you what it is. It's a vector that goes from the origin. Technically, it doesn't have to go from the origin, but for what we're doing here, just say it's from the origin to where the person is at a particular moment of time, or where the object is at a particular moment of time. So this particular moment of time, the person's here, right? So you just draw a vector that goes from the origin to where the person is at that time. And there's a t here because it depends on time, right? At some point in time, the person was here. So the position vector is like this. At some point in time, the person was here. So the position vector is like this. So the position vector changes all the time, depending on where the person is, right, at different moments of time. That's why there's a t there. So, but it's nothing magical, right? It's just another vector, right? So how do you write a vector? You write a vector in component form, right? It's a little bit in the x direction, plus a little bit in the y direction, right? So basically, if you know the x and y coordinates of this person, correct? Then when you make, let me just show you, I'll erase this, but you make this into, vector. So this is the x coordinate, right, of the person at this moment of time. This is the y coordinate of the person at that moment of time, right? So basically, the r vector would be xt, which is the x coordinate at that moment in time in the x direction, plus the y coordinate of the person, right, in the y direction at that particular time. Does this make sense so far? It's just another vector that is actually being used to describe how a person moves. Okay, so this makes sense, right?
Yes.
Okay. So, sorry. This is the position vector, not the displacement vector. Sorry, I misspoke when I said this. This is the position vector, right? So this is the position vector, right? It's a function of their position, right? Okay. So then what we can do is describe what's known as the displacement vector, which is related to the position vector. So the displacement vector is a vector subtraction of where the person was at one point in time compared to where he was, where the object is at a different point in time. It could be a person or an object. So in other words, at one point in time, the person, say, was here. At some other point in time, it's here. So basically what you do is you find the position vector where the person started, right? Call that Ri. And then you find out where the position vector is where he ends, call that Rf. And you subtract those two things, and that gives you another vector, which is known as, that is the displacement vector, right? That's what I wanted to say. So how you would write it out mathematically, I mean, it's a bunch of math, but it's pretty easy to follow, right? So the initial vector, Ri, is just, the position at some initial time, so that's ti, right? Xti, Yti. The final vector is the final time, and then you just subtract those two things. This delta thing comes up all the time in physics, by the way. So this triangle is a delta. We say delta all the time. So delta R is the displacement vector, and a delta, this thing here, always means you take the final quantity and subtract the initial quantity. So when you see it in front of a delta R, it means take the final position vector and subtract it from the initial position vector, right?
Delta means change.
Yeah, it means change, right? How much it changes from initial point to the final point. So this is the definition of the displacement vector, right? It's a new vector related to the position vector. And you could just, you subtract it. How do you do vector subtraction? You just subtract the components. So mathematically, you're subtracting these two things, and you're subtracting these two things to find the x and y parts of it. But this, by definition, is the change in horizontal position, right? xi minus xf, or xf minus xi, and this is yf minus yi, which is the change in vertical position. So this gives you a new vector called the displacement vector. Does it make sense so far? And we'll do examples, but we're going to do things. So yeah.
Would the magnitude of the displacement vector tell you how far apart you moved?
Mm-hmm.
Okay.
Yeah, we're getting to that. So what I have here is just, it's hard to see, but there's a dot here. And if I go forward in time, this dot moves around this 2D plane, right? So basically, this vector here is the position vector at that moment in time for the dot, right? So you can see it changes because the dot is at different places at different times, right? So that is the position vector at different times. Now, what I'm doing here is So, okay, so this dot goes from here to here. So this is the final position of the dot, right? But at one point the dot will say here, right? So this is the initial position vector, right? This is the final position vector, what I just described. This thing here is the displacement vector, right? It's the difference of those two vectors. If you subtract them, this is what you get. So I'll show you where this comes from in a second. Actually, I should have gone through the next thing before I showed you this. If you solve for the final position vector, you get here. If you solve this equation here for RF, right, you just add RI to both sides. So basically what we're doing here is if you take RI and you add delta R, which is the displacement vector, to the end of it. So how do you add vectors? Remember from yesterday? You put one vector at the end of the other vector, right? So what I'm saying here is if you start with RI and you put delta R at the end of it, that gives you the position, the final position, right? So this is where this graph comes from. I should have showed you that step before here. So here's Ri. If you add delta R to the end of it, that gives you RF, right? So this is delta R. This is the displacement vector, right? That's what it is. And does this make sense so far? All right, so I'm going to do a few things before I do an example. Well, let me see. Hold on. I got to see my example. I can maybe start it now. Yeah. So there's a bunch of, like we did yesterday, right? There's a bunch of parts to this example. But we can start by doing displacement vector first, right? And then we'll go back to the notes and do more things with the example. So let's start the example now, so it makes more sense. All right. So suppose we're given the following position vector. All right. So this describes what an object is doing at every moment of time. It describes where the object is. So the units, I'll explain the units as I go, right? But let me just write down the vector, and then I'll tell you what these things are. Okay, so I should have mentioned this when I was first describing it. Position is measured by coordinates, and coordinates are basically distances. So basically, position vectors are distances. So typical units of distances are meters, right? So you want your answers to be in meters, meaning the x-coordinate to be in meters and the y-coordinate to be in meters. This is why this is in meters, because the cosine is no unit. So you just get an answer in meters for the y part. Now, this thing has to be, so this is a t squared here, right? So it's a function of time. So if you square time, which is typically measured in seconds, it cancels out the second squared here, so you get units of meters also for the x component. That's why I wrote it like that, right? So the point is the x and the y part should both be measured in meters, right, for this position vector thing. Okay, so this is a position vector. You know, if you put in different t's, you get different positions, right, where the object is, right? This is basically x and y components of the object. So the first thing you're going to ask is, what is the displacement vector from 0 to 3 seconds? In other words, at one point, the object is somewhere at 0 seconds. And then at 3 seconds, it's somewhere else. So the question is, what's the displacement vector from 0 to 3 seconds? So what we got to do is we got to figure out where the object is at 0 seconds, or what the position vector is at 0 seconds. Then we got to figure out what is it at 3 seconds, and use that to get the answer. So, all right. So Ri, you could say the initial vector is the position vector at 0 seconds, right? So what is the position vector at 0 seconds? All right. So what is this? What is the x part of it if t is 0?
5.
No. 0, right? So there is no x part. It's just, it basically means the object starts on the y-axis somewhere, right? Or negative y-axis. So minus 2 meters times the cosine of 0, right? What's the cosine of 0? 1, right? So I wrote it with the 0 there. You don't have to write the 0 if you don't want to. You could just put minus 2 meters y hat, but I just put it there. So this is basically the initial position of the object. It's at 0 minus 2 meters, right? This is where it starts. Okay, so then what we're going to do is figure out where is it at 3 seconds, which is the final position vector. So it's minus 5. Okay, so this is just, I mean, you can figure this out pretty easily. It's just 9 times 5, right? So it's minus 45, right? What about this? So this is, the argument of cosine is what? It's 3 pi, right? See, the seconds cancel out. Seconds cancel like units, right? Seconds divided by seconds is just nothing. So the cosine of 3 pi, does anyone know the cosine of 3 pi? Yeah, negative 1, right?
Yeah.
So it's just negative 1 times negative 2, which is what? Plus 2, right? Okay, so that means the final position vector is minus, so I'll show you how the units work out. So it's minus 45 because it's 9 times 5. But it's meter per second squared. When you square the 3 seconds, you're squaring 3, which is 9, and the seconds. So you get seconds squared, right? The units squared too. So the second squared cancels out because you get meters per second squared times second squared gives you just meters, right? This is what it should be. Oh, sorry, y hat. So you get minus 45 meters x hat plus 2 meters y hat, right? So this is the final sort of position of the object. It's at negative 45 meters is the x-coordinate, and the y-coordinate is plus 2 meters, right? That's what that tells you. All right, so does this make sense so far?
Mm-hmm.
So now we have to find the displacement vector. So this is this thing called delta r. It's just the difference of these two vectors. So how do you find the difference of the vectors? Well, you subtract their components, right? So this one, the x part is easy, right? It's minus 45 meters minus 0, because it started at 0, right? And the x part was 0. And then plus 2 meters, the y part here is 2 meters, minus the initial y part. So you got to be a little bit careful with your signs, right? So what does it wind up to be? Well, it's minus 45 x hat plus 4 meters y hat, right? So this is the position vector, the displacement vector, right? From 0 to 3 seconds. All right, so does that make sense? All right. We can do another part while we're here. So you can, if you have the displacement vector, you can apply what we did yesterday here. So you can find the magnitude of the displacement vector, and you can find its direction. This is something else you can do. So how would you find the magnitude of the displacement vector? It's what we did yesterday. If you know the x and y components of a vector, how do you find its magnitude? No. Yeah, these things form right triangles all the time, right? So you take the x part squared, add to the y part squared, take the square root. Right, so the magnitude of the displacement, which is just delta r without the vector sign, is, you don't have to write negative 45 because you're squaring it. But so, as to not to be confusing, I'm writing it as negative 45, but it's really, the same thing as 45 meters squared. You just square the components, add them together, and take the square root. So you get 45.17 meters. So what does that tell you? It basically tells you the length of the line that connects the starting point to the ending point, right? Because the vector goes from the start to the end, right? So the length of the vector is just the length of the line that connects the start to the end, right? Okay. All right, so does that make sense? It's just basic vector stuff. Okay, we also have to find the direction. By direction, I mean the angle, right? That's what I mean by direction. So you have to do basically what we did yesterday. Like, you don't have to do this if you're really good with this stuff and you can visualize it in your head. But when we first start doing this, I'm going to do it like this, by sketching it. Like I said, if you can figure it out in your head, you don't need to do this, then you don't have to do it. But since you just started doing this stuff, I'm going to sketch it out. So what I mean by sketching it out, it's negative 45 meters, and the x part is negative 45, right? So you have to go 45 meters to the left, and the y part is plus 4 meters. So when you sketch it out, it looks like this. It's 45 meters in the negative x direction. So this is 45. I'm just writing it, just the amount. It's negative 45, but the fact that I'm drawing it to the left means it's negative. And then it's 4 meters up, so it's not quite to scale, obviously. 45 should be a lot bigger than 4. But this is the displacement vector, right? So what you can do is you can find the angle inside here all the time, which is known as the interior angle. So how do you find that angle?
Arctangent.
Yeah. Yeah, it's the opposite side, which is 4 meters, divided by the adjacent side, which is 45. So it's meters cancel out, right? So it's 4 over 45, which isn't that great of an angle because x is so much bigger than y, but still, you get 5.08 degrees, which is fine. But the answer I usually always ask for, say on a test or on Canvas, is going to be the angle from the x-axis, which I called phi last time. You can call it whatever you want to call it, but I always usually ask from the x-axis, right? Not the y-axis or whatever axis. So what would phi be?
Would be -5.
Yeah, it's 180 degrees to get to the negative x-axis, right? So you have to subtract 5.08, so it's 174.92. So the displacement vector would be 45, whatever it was, 0.17 meters at an angle of 174.92 degrees from the positive x-axis, right? That's another way you can write it. All right, so does that make sense? That's how you figure out displacement vectors, right? You figure out the initial position vector, the final one, and then you do this. So you can write it down both ways, right? You can ask for this, or you can ask for the magnitude and direction, right? That's how you do both of them. Okay, so let's go back to the notes, right? So everyone's clear basically what the displacement vector is, right? So it's a vector that points from the initial vector to the final vector. The magnitude of it is length of the line that connects the initial position to the final position. And the angle of it is how you get from the initial point to the final point. Yeah.
So was the purple line in the beginning distance? Is that just the total distance?
Yeah, so let me go back here. So, yeah, so displacement and distance are not the same thing. So basically, let me go back to the demo here. Okay, so if you start here, it's a little bit hard to see. Let me make it a little bit bigger. There's no view. All right, so I can just make this bigger. don't know where the view thing went. Oh, there it is. Okay, so let me make this bigger. All right, this is huge. Okay, so suppose you just look at the end of this. So it starts here, right? Suppose this is where it starts. It ends here. So the displacement would be this red thing here, right? So the magnitude of displacement is how long this line is, right? So basically it's just the distance between where it starts and where it ends, right? The angle of this thing is how you get from the start to the end. Now, the distance that it goes would be the blue line here. So the distance that you go, see it's the length of this line here, is not the same thing as the magnitude of displacement, right? They're two different things. Does everyone get that? So this would be what's known as distance, which we'll talk about in a bit. Actually, that's the next thing I was going to talk about. This is the displacement, right? They're not the same thing, right? The magnitude of displacement, I should say. Yeah.
That's delta R, right?
This red thing is delta R.
Right.
This blue thing would be the distance that you go, right? The length of that arc. We don't talk about distance that much. It's not really important. So, but there is a difference between the two, right? Okay.
Why are we finding the displacement then? What is it telling us?
Well, right now it's not particularly important, but when you start defining other things in terms of the displacement vector, it becomes important. That's why we're doing it, right? Okay. So that's the next thing I'm going to get to. All right, so here it is here. Yeah. So this is where I mentioned distance. So distance, like I said, is the total length of the path traveled, right? Which is not the same thing as the magnitude of displacement. Okay. So now we're going to start using displacement to define something else. So the first thing you can just talk about, which is sort of something you're more familiar with, is called something called speed. But we don't actually talk about speed that much. But the reason why I'm mentioning it is because it's easier to introduce velocity if you sort of understand what speed is first, right? So speed, average speed, is basically the total distance that you go divided by the time it takes you to travel that distance. This delta t is how long it takes you to get from point A to point B, right? So you go back up to this picture here. The distance that you go is this, how far you go along this path from here to here, right? So if you figure out what this path is, which is kind of hard to do, you have to do, some calculus to figure it out for a general path. If you divide the length of this blue line by the time it takes you to get from this point to this point here, that defines what's known as your average speed, right? Okay. Which I call S average, right? That's your average speed, okay? Does everyone, yeah?
Is the D displacement or distance?
No, D is distance.
Okay, distance.
Yes, D is distance. Okay, so the reason why I bring this up is because then you can define something that's kind of like speed, which is called velocity, average velocity. So the average velocity is something we'll be using way more often than average speed. In fact, we almost never use average speed. But the average velocity is sort of like average speed, but instead of using distance, what we use is the displacement, right? The displacement vector divided by the time it takes to get from point A to point B is what's defined as the average velocity vector. So it's a vector, right? Because displacement's a vector, so when you divide a vector by a scalar, so basically what you're doing is dividing the displacement vector by a number, which is a time, and that gives you another vector. Now this time is always a positive number, right? So the time goes forward, right? So basically where you start and where you end up, the time it takes to get to the end is always greater than the time it takes that you start with, right? Because time always goes forward. So delta t is the difference of the two times, or basically the time it takes to get from point A to point B. So this is always a positive number, right? So basically what you're doing is you're taking the displacement vector and you're dividing it by a positive number. So does anyone remember what happens in this general case? So if you have a vector, we talked about it yesterday. If you have a vector and you multiply it or divide it by a positive number, what happens to the vector? Yeah, the magnitude changes, right? It gets longer or shorter depending on what you're doing. But if it's a positive number, does the direction change? No. So what this is telling you is the average velocity vector is in the same direction as the displacement vector, but it's not the same vector, right? Because you're dividing delta r by delta t, right? So this is average velocity, right? this is how it's defined. So the displacement vector divided by delta t. So in component form, what you do is you take the x part of the displacement vector and you divide it by the time it takes to get from point A to point B. And you divide the y part of the displacement vector by the same time. And that gives you the y part of the average velocity vector. So this is, well, let's do an example, right? So let's do an example of finding the average velocity vector and see how it works out, right? So let's continue that example we were just doing. Then we'll start putting all this stuff together. Okay, so let's continue this example, right? We found the displacement vector. So what we can do, what part is this? C, right? Okay, so the next question is, what is the average velocity vector from 0 to 3 seconds? Okay, so like I just said, this is how you find the average velocity vector. So this means you take, this is basically, x. Delta x is basically the x part of the x component of the displacement vector. And delta y is the y component of the displacement vector. That's what we did in the last part A or whatever. So if you want to find the average velocity vector, written as a vector in component form, what you first do is you have to find delta r. We did that already. So basically the x part of delta is minus 45. This is delta x, basically. The y part is 4 meters. That's delta y. So basically all you do is divide this by 3 seconds and divide this by 3 seconds. And that gives you your average velocity vector. That's it. So this is minus 45 meters divided by 3 seconds plus 4 meters, right? So what do you get? You get negative 15 plus 4, I'm just going to write it as 4/3. I'll explain the units in 1 second. Let me just finish writing it. So 4/3 is 1.33 if you want to write it as a decimal, but it's better just to leave it like that. Okay, so the units, all you do is divide the units from delta x and delta y by the time, which is measured in seconds, so you get meters per second, right? So basically average speed, average velocity, and velocity when we get to it is going to be measured meters per second or length per time, right? That's the units. All right, so does that make sense? That's the average velocity vector. What that tells you is on average, you were going in the negative x direction at 15 meters per second, right? And you were going the y direction at positive 4/3 meters per second, right? To get from point A to point B, right? Your average velocity. So the bigger your average velocity is, the more displacement you cover in the same amount of time, right? You're going faster, essentially. Okay. So you can also, this is one way to write the vector, but you can also do this too. What's the magnitude?
45.17/3.
Almost. Yeah. All right, so how do you find the magnitude of a vector again?
It's like the height of the
Right. Once again, you don't have to write the negative because you're squaring it, but I usually write it so it doesn't confuse people. But you put this in your calculator and you get 15. So this is easier to comprehend. So basically what it means is on average you're moving at 15.06 meters per second to get from point A to point B, right? This is on average how fast you were going. That's one way to figure it out. You can also figure it out from, it's something that we talked about yesterday. If you take a vector and you divide it by a number, right? The magnitude of the vector is the magnitude of the original vector divided by the number, right? So basically what I'm saying is if you know the magnitude of delta r, which is what we did in the last part, which is 45.17.
Okay, so.
Oh, is that what you were saying?
Yeah.
Okay,
that
sorry.
does work.
Yeah, sorry, I thought you were saying something else. Either way, you get the same answer, right? It doesn't matter. All right, so does that make sense? We also have to find the direction, but this is easy. I just mentioned how you find the direction. So you're dividing delta r by a positive number. So what's the relationship between the direction of VAB and delta r? It's the same direction, right? The average velocity is the same direction as displacement, right? So you don't have to recalculate. I mean, you can if you wanted to. You could do what we did in the last part again. But the point is, if you know that, if you're confident that delta r is in, the direction for delta r is correct, then VAB is in the same direction, right? As delta r. It's the same direction. 174.92 degrees from the x-axis. All right. Does that make sense so far? All right, because all this stuff builds on one another, right? So if you don't understand one step, it's a problem, because then you can't understand anything else. All right, does this make sense so far? Okay, so let's go back here. Okay, so now we know how to calculate the average velocity vector. We know the position vector, the displacement vector. So the next thing we're going to talk about is the velocity vector itself. So this is the velocity vector at any moment of time, right? The average velocity is, on average, how fast you're moving and what direction you're going from point A to point B. The velocity vector is, at any moment of time, exactly how fast are you moving and in what direction are you moving. So that's the next thing we're going to talk about. Okay, so basically, what you're trying to do is you're trying to do a limit. So basically, if you start at one time and then you go to a slightly bigger time, right? Your difference of time between these 2 points is very small.
Like, is this instantaneous?
Right, you get to be the instantaneous velocity. So basically, you're taking the limit as delta t goes to 0 of the average velocity vector, right? It's the definition of a derivative, basically, right? So you start zooming in on the velocity vector at a certain moment of time. So the limit as delta t goes to 0 of delta r over delta t is this new thing called the velocity vector at this moment of time. And it's basically just the derivative of the position vector. So it's r prime at t. So how would you do that? You just take the derivative of the x component of the position vector and the derivative of the y component of the position vector. This gives you the velocity vector. Now, if you zoom in on this, let me show you something here. All right. So what I'm going to do is I'm going to make these 2 points really close together and try to see what happens to the red arrow. Although, all right, so I'm going to go back and forth here. All right. So here, they're pretty far apart, right? But then I start bringing them closer together. And what happens to the red arrow? Can you see it? I can't tell you. I have to, I can't put both of them, but yeah, it gets shorter, but what happens to the direction, I should say, of the red arrow?
It changes.
It changes, yes, but when it becomes really small.
It matches up with the position.
Yeah, what I'm trying to say is when the time is really small, the displacement vector is basically tangent to the path,
Right. Okay.
right? So basically the velocity vector is tangent to the physical
So that's
path.
the derivative of the
Right,
position.
it's the derivative of the position. So that means the velocity vector is tangent to the physical path, right? That's the direction of the velocity vector is tangent to the path. That's what I'm trying to say. Okay. All right, let's go back to the example. And So all that's explained there. When you see the notes tonight, you can read that. Let's go back to this example and do something with velocity vector. Okay. So this is part E, right? So the question is, what's the instantaneous velocity vector? Which is the same thing as a velocity vector at any moment of time. So at any moment of time, you can figure out what the velocity vector is. Okay, so this is just the derivative of the displacement vector. So just so you know what the displacement vector is, because we kind of forgot it, it was a few minutes ago, I'm going to copy it down here. This is the displacement vector. Okay, so what you need to do is you need to take the, yeah.
I don't know if this was already asked, but by instantaneous velocity, do you mean like terminal velocity? Like what-
No, terminal velocity is something else. Instantaneous means at any instant of time, what is the velocity vector? So what it means is, what is the velocity vector as a function of time?
Okay, so like that's kind of like the
Mm-hmm. Okay, so this is R. So basically what you need to do is you need to take the derivative of the x part and then the derivative of the y part with respect to time. And that gives you V. So let's do that. So V of t, so what's the derivative of negative 5 meters per second squared t squared with respect to t?
Which is negative 10 t.
Mhm. So the units don't change, you just keep them there. But there's a t there now, right? Instead of a t squared.
So keep the units with the number.
Yeah, you don't change the units, right? So that's the x part, right, of the velocity vector. And then you have to take the derivative of this, right, with respect to time. So there's no t here, but you have to take, sort of a chain rule here, right? You guys remember, like the chain rule? You have to take the derivative of the inside. So what do you take the derivative of this with respect to t, what do you get? So pi second times t, the derivative with respect to t, what do you get? You just get pi per second, right? It's kind of weird, but so you get 2 meters pi per second, right? That's the derivative of the inside of cosine. And then what's the derivative of cosine?
And it has this negative sign,
Right.
so it has to be plus.
Yeah,
10
but I'm
meters.
just writing it like this right now. Oops. If I write something down wrong, just let me know. Sometimes I write too fast and I forget something. But this is the derivative, right? So this is really, I'm just going to rewrite this. So this is really like plus, right? And then I can get rid of this here and move this over, right?
Okay, pi over seconds is a constant.
Yeah, it's like
So
3
that's
point,
a
it's
constant, so we just-
3.14 per second, right? That's basically what it is. So this is the velocity at any moment of time.
Yes.
All right, so does this make sense?
Yeah, totally. No. I think you need a bit of something. This is a vector thing with calculus. It's very interesting.
So this is a function of t. So that means at any moment in time you can figure out what the velocity vector is. So for instance, we can ask, what's the instantaneous velocity? It's basically the velocity, right? Let me just say, what's the velocity? Because it may be a little bit too complicated. Vector at t equals 3/2 of a second, right? So this is at any time you can figure out, right? This is a general equation, but you can ask a specific time at 3/2 of a second, 1.5 seconds, right? What is the velocity vector, right? So this is the general velocity vector here. I'm just going to copy it down. So you just plug in t equals 3/2, right? and you
Yeah.
see what you get. So that's the x part of it, which we'll figure out in a second. Oops. All right, that's the y part. So let's simplify this. So this becomes what? So this is minus 10 times 3, which is negative 30 divided by 2, right? So what does that become? Negative 15. So what happens to the units? There's a second here. There's a second here. So one of the seconds on the bottom cancels out. So what are the units?
Meters per second.
Right. So it's negative 15 meters per second.
Plus.
Yeah, well, there's a question.
Was it negative sign?
Yeah, because the original R was negative. Right?
So meter.
Oh, I see.
Yeah.
Okay.
Yeah. So, no, but sometimes I forget things. So sometimes I put an extra negative sign. So if I do that, just let me know. So this is negative 15 meters per second x hat, right? So then you got to figure out the y part. The argument,
Negative one.
it's just 3 pi over 2.
Right.
So it's the sine of 3 pi over 2, which is, yeah, it's negative 1,
Right.
right? So you get,
So negative 2 meters.
yeah. It's kind of weird, but pi is just like 3.14, right? So it's 2 meters times 3.14 divided by seconds, right? All right, so does that make sense? This is the velocity at 3/2 of a second, the velocity vector.
This doesn't describe, this isn't the tangent line at that point on the position, right? This is not,
So this is the next part. So what you can do with this is you can use it to figure out exactly how fast something is moving at this moment in time. To do that, that's the magnitude of this velocity vector. And you can find the angle of this velocity vector, and that would be the angle that that object is moving at that particular time, because the velocity is tangent to the path, right? So the thing comes around like this, you know, in the picture I just showed you, it was going around like this.
yeah.
So this point is going sort of in this direction.
So we're using vectors to find out all of that stuff. Like
Right.
the angle, how fast it's
Mhm.
not just the regular calculus one
Right,
information.
right.
Okay.
Which is the next part. This is the next thing we're going to do. So, what's the magnitude of what's the magnitude of the velocity vector at 3/2 of a second and its direction? So the magnitude is how fast the thing's moving at this time, right? That's exactly what it tells you. So how do you find the magnitude? If you know the x and y parts again. That's what we did a couple times already. Yeah.
So negative 15.
Technically -2 again, but you don't need to write the negative if you don't want to because you're squaring it, but they're both negative. And so that should be, if I did it right, 16.26. Right, so this is just, I can show you quick. So it's 15 squared plus 2 times pi, basically, right? Squared, and then you gotta take the square root.
So this is 9.
16.26, right?
This is the instantaneous velocity?
Yeah.
The magnitude.
This is how fast you're moving at this
that
time,
point.
right?
Okay.
Mhm.
Magnitude.
Yeah.
So we don't plug in 3 because it's square root the square of epsilon components of the velocity vector.
Yeah. No, this is just the magnitude of v at 3/2 of a second, right? Which is the magnitude of the velocity vector at 3/2 of a second, right? All right, so how do you find the direction? Well, you should start by sketching it, right? Okay, so it's 50 meters in the negative x direction. So I'm just going to write 50 meters per second, I should say. But I'm just going to, I'm not going to write the negative. The fact that I'm going to the left means that it's negative, right? So it's a little bit weird because usually you're used to drawing lines, measuring them with distances, but it's not really a distance, it's a meter per second thing, but you can just leave it like that. And then you have to go down because it's negative. Right, the y part is negative. And this is, you go down 2 meter pi per second. And this is the velocity vector at that point. So how do you find this angle, the angle inside? It's the inverse tangent of the opposite, which is 2 meter pi per second. And then the adjacent side, which is 15 meters per second. So the units should cancel out. The meter cancels out that meter, the second cancels out the second. So it's basically 2 pi divided by 15, which is like 6.28 divided by 15. Inverse tangent of that, which is 22.73. So that is the interior angle. But I always ask for this angle again, right? From the positive x-axis, say from here to here. So how would you find that angle?
You add that to your angle?
Yep. So it's 202.73 degrees from the positive x-axis, right? So this tells you, right, how fast you're going at that point and what direction you're going at that point, right? So you're going at this direction and you're going this fast, right? 16.26 meters per second, right?
So you'll make that to 202.73, that angle.
Yeah, from the x-axis, right?
Okay, cool.
All right, so does that make sense? So does everyone understand what velocity is, right? So obviously the faster, the bigger v is, the faster you're moving, right? Okay. All right, so everyone's good, right? Because we have to go on from here. Everything builds on one another. Okay, so the next thing we're going to talk about is the acceleration vector. And the one thing I should say with velocity vector, before I go to acceleration. So it's a little bit weird, but if you think about it, it makes sense, but it's a little bit weird at first. This is the average speed, right? It's the distance divided by the time, right? The length of the path, right, divided by the time. The average velocity is the displacement divided by the time, right? So they're not the same thing. However, when you take the limit that delta t goes to 0, right, that we use to define the velocity vector, what's true about displacement and distance if this is basically an infinitesimal thing?
What was the question again?
So as you take the limit as delta t goes to 0, and this becomes really small, what's the relationship between the displacement, which is delta r, and the distance, right? The length of the line between those two things. What do you think? They're both the same thing, correct? Because you get this tiny little distance, right? So the displacement just goes over that line, so it's the same thing, right? The magnitude of the displacement and the distance are the same quantity. So that means that when you talk about the velocity vector, right, the magnitude of the velocity vector is the same thing as the instantaneous speed at that time. because delta r and d are the same thing. Well, the magnitude of delta r and d are the same thing, right? So a lot of times we say, we talk about speed when we're talking about velocity, but what we really mean is just the magnitude of the velocity vector, right? Is the speed. It's how fast you're going at that time, right? Okay. Does that make sense? Okay. You got to think about it a bit, but it makes sense if you think about it. All right, so the next thing we're going to talk about is, I'll give you a break in like 10 minutes, right? You can take a break. Or 5 minutes or so, 5 to 10 minutes. But the next thing I want to talk about, introduce first before the break, is the what's known as acceleration. We're going to talk about average acceleration first, and then we're going to talk about instantaneous acceleration. So what is average acceleration? So acceleration is kind of an important thing in physics because it's related to forces when we get to forces. So you kind of have to understand what acceleration is and how it relates to velocity. Okay, so this is the definition of average acceleration. So we just figured out this velocity vector, right? And typically velocities change with time. In other words, we just did an example. We found the velocity at 3/2 of a second, right? But if I picked 0 seconds or 2 seconds, you could have a different velocity vector, right? So it's changing all the time. So basically, if you figure out the velocity vector at some point, like say 0 seconds, and then find the velocity vector at say 2 seconds, and you subtract those two vectors and divide it by the time it takes to change from one to the other, that is what's known as the average acceleration. That defines the acceleration. So the average acceleration is related to how much the velocity is changing with time, right? Okay. So how you would figure it out, the average acceleration, is you would first figure out what the final velocity vector is after some time, what the initial velocity vector was, and then subtract their x components divided by the time, and subtract their y components divided by the time. That gives you the x and y parts of the average acceleration vector, right? So the average acceleration vector is a lot of people think about velocity when they're talking about acceleration. But you got to remember, acceleration is how much velocity changes by, right? So if velocity doesn't change, what's the acceleration, do you think? If the velocity never changes, so it's 0, right? But what does that mean? It means that not only are you going the same speed, you're also going the same direction, right? Because velocity is speed and direction, right? So if you're always going in a straight line at the same speed, then the acceleration is 0. Otherwise, it's not 0, right? Okay. Now, if you take this equation here and you solve it for the final velocity, right? So see, it's AAV is VF minus VI divided by delta t. So what I did is I multiplied by delta t. That's VF minus VI, and then I added VI to both sides. I get this equation here. This tells you the direction of the average acceleration. So what does this mean? Okay, so if I take VI, so this is the initial velocity vector, and I add AAV times delta t to it, right? So AAV times delta t is a vector that points in the same direction as AAV, is what I'm trying to say, because delta t is a positive number, right? We went over this when we talked about displacement velocity. So if I multiply delta t by AAV, it just makes AAV bigger or smaller, but it points in the same direction as AAV. So VI plus AAV delta t, which is this thing here, gives you VF, right? When you add the vectors, right? VI plus this thing gives you VF. So what I'm trying to say is AAV points from VI to VF, basically, right? You have these two velocity vectors, VI and VF, and AAV points from the end of VI to the end of VF, right? That's the direction of AAV. The units of AAV is units of velocity divided by time. So what's units of velocity? We just did it. Typical units of velocity. Meters per second. So if you divide it by time again, what do you get, do you think? Meters per second squared, right? So those are typical units for acceleration. All right, so we'll do some examples with acceleration, but you can take a 10-minute break, and then after the break we'll do examples with acceleration. All right, take a break, come back at like 2:20. All right, so now what we're going to do is an example with average acceleration. So let's go back to this. We're just going to continue with this example here. So the next thing we're going to do is ask, what's the average acceleration vector from 1 to 3/2 of a second? In other words, from 1 second basically to 1.5 seconds. Okay, so the average acceleration vector we just learned before the break is, sorry, I can't write an A. Okay, so it's basically the final velocity vector minus the initial velocity vector divided by the time it takes to change from the initial to the final. So in this case here, the final velocity vector is what the velocity is at 3/2 of a second. The initial velocity vector is what the velocity was at 1 second, right? Because it's 1 to 3.5 to 3/2 of a second. The time it takes to change to get from the initial to the final is just the difference. Sorry, just the difference of the times, right? It takes a half a second, right, to go from VI to VF. So, you know, in essence, it's just, this is the average velocity vector. Sorry, I forget to write the vector. So you could, if I forget to write something, just let me know. So you're essentially dividing by a half a second, right? Because the time difference is a half a second. Okay, so we know what V of 3/2 is of a second. We just found it here, right? Part F. So this part is done, right? I mean, we don't have to do this step, is what I'm trying to say. But we need to find the velocity at 1 second, right? Because we haven't done that yet, right? We found the velocity at 3/2 of a second. We didn't find it at 1 second. So we need to determine all right. So let's do this. First, I'll have to go. So this is the velocity vector in general. Part F as well, right? Or part E is when we found it. All right, so basically what we're going to do is we're going to stick in 1 second into here and see what we get. All right, so let's look at the y part first. The seconds cancel out, and you just basically get pi here, right? Pi divided by seconds times 1 second is pi. What is the sign of pi?
0.
Yeah, 0. So the y part is 0. There is no y part. It's just moving in the x direction at 1 second. So, you know, it's just 1 second. So it's minus... sorry, it's not squared. Sorry. I do that every once in a while, right? I write something down wrong. So let me know if I do that. Okay, it's not squared, right? It's just 1 second, right? So it's just minus 10 meters per second x hat plus 0 y hat, right? So that's the velocity at 1 second. It's just moving in the x direction at negative 10 meters per second, right? That's what it's telling you. Okay, so the reason why we did that is because we want to find the average velocity, average acceleration, sorry, not average velocity, which is this, right? So that means we need to subtract the x part of the average acceleration, of the velocities, I should say. So it's the VF is the 3/2 and VI is the 1. So it's basically this minus that, right? So it's negative 15 minus negative 10. Divided by 1/2 of a second, right? And then the y part is just the final, it's VF, which is 3/2 of a second, which is negative 2 meter pi per second. Actually, borrow this. minus 0, because there's nothing for the y part. Also divided by half a second, right? Divide both of them by the same delta t. So then you can just simplify this. You got to be a little bit careful, right? Because it's really negative 15 plus 10, which is what? What's negative 15 plus 10? And then divided by 2. Divided by 1/2, which is the same thing as multiplied by 2 is what I meant to say. So it's negative 5 times 2, which is what? Meters per second squared, because you get meters per second divided by second, which is meters per second squared. And then minus, so that's the x part. And then it's really negative, because this is negative. 2 meter times 2, right? Which is 4 meters, right? Pi, once again, per second squared. All right, so does that make sense? Yeah. What was it? From here to here?
Yeah, if you multiply by 2.
Yeah, because you're dividing by 1/2,
Okay.
right? Same thing, yeah. All right, so does that make sense? That's the average acceleration vector at that point. Now you can find the magnitude of it and the direction, but I'm going to skip that part this time. But how would you find the magnitude of it if I asked for the magnitude? Yeah, it's this thing squared plus this thing squared, square root, and then how would you find the direction? You sketch it out, right? Draw the thing, same thing. All right, so does that make sense? That's how you find it, yeah.
So what was that? Like, what is the answer? Like, what is that? Or what were we finding?
The average acceleration vector, right? So that's the vector, yeah.
But can you also look why you got -10?
So this is minus 15 plus 10, which is negative 5, times 2, because you're dividing by 1.
So that's a negative sign, then negative 15 squared minus negative 10.
Right.
Oh, okay.
Yeah. All right, so this makes sense so far? All right, so the next step we can do is do something that we did for average acceleration, average velocity and velocity, which is to find the instantaneous acceleration, basically the acceleration at any moment in time, which is the same thing you did for velocity. You take the limit as delta t goes to 0 of the average acceleration, which is delta v over delta t. And this gives you the acceleration vector at any moment in time. It's an instantaneous acceleration vector, right? Or just the acceleration vector. So what you do is you take the derivative of the velocity, instantaneous velocity vector with respect to time, and its x part, to find the x part of the acceleration vector. And you do the same thing with the y part, right? To find the y part of it. This is something else you can do. Sometimes you know the position vector and you just want to find the acceleration vector right away. Because the a is basically dv dt and v is the r dt, right? This is what we did a couple of minutes ago or before the break. Then basically it also means that the acceleration is the second derivative of the position vector with respect to time, right? You can do it all in one step if you wanted to, so you could do this instead too. But we're going to focus on this part first, right? So this is the next step we're going to do. Let's go back to the example and calculate the acceleration vector. What is this, part J, I think? Okay, so. Okay, so this is the next question. What's the acceleration vector at 3 seconds? Oh, sorry. No, sorry, that's the next part. Sorry, what's the acceleration vector? Sorry. This is part I, sorry. The next part is at 3 seconds, my bad. Okay, so what's the acceleration vector? Okay, so AUT is basically dv dt, or you can write it like this. Sometimes it's written like that, right? The derivative with respect to time of v. And because we probably forgot what v is, so let's go back and copy down what v is so we can do this. We did this, sorry, here, right, in this step, step E, party. Okay, so what we need to do is take the derivative of this with respect to time. Okay, so A at t is the derivative of the x part, right? So what do you get when you take the derivative of?
Negative 10 meters per second.
Yeah, it's pretty easy for this one, right? The t just goes away, right? So it's minus 10 meters per second squared with no t, right? So that means the x part doesn't change, right? It's constant. All right, plus we got to take the derivative of this whole thing, right? The y part. So once again, you have to do the chain rule again. So what's the derivative of pi per second times t with respect to t? Pi per second, right? So this becomes squared, right? Because you have 2 pi per seconds, right? And then you're going to take the derivative of sine. So what's the derivative of sine?
Cosine.
Cosine, right? So this is the acceleration vector, right, at any moment of time, right? If you plug in different t's, although the x part doesn't change, but the y part does. If you plug in different t's, that gives you different acceleration vectors, right? All right, so does that make sense?
Mhm.
All right, so then we can do this. So this is part, what was it, J? So what's... So just an example, right? You can pick a time to find what the acceleration vector is at 3 seconds. So the x part doesn't depend on t, like I said, right? There's no t in there. All right, so the seconds cancel, and this is just basically, yeah, cosine 3 pi, right? There's a y hat here, I forget the y hat. Okay, so then the cosine of 3 pi is just -1 again, right? So this becomes minus 2 meters pi per second squared y hat, right? So that's the acceleration at that moment of time, right? At 3 seconds.
I'll be the second square.
Yeah. meters per second squared. All right, just to do one more example of this, and then we're done with this example, but just one more time. What's the magnitude? Should know how to do this pretty well by now, I would hope, but. So what's the magnitude of the acceleration at 3 seconds in its direction? So how do you find the magnitude?
Okay,
Yeah.
10 meters per second squared.
Yeah, it's a little bit messy because there's pi per second squared, then you gotta square that, and then take the square root, but yeah, it's a little bit messy, but you get the idea. It's 22.13. And it's actually meters per second squared. So first of all, the units should be meters per second squared, but the question is how does it come out through here? So when you square the meter per second squared, you get meters squared per second to the fourth, right? Both of these things are meters squared per second to the fourth when you square them, both of them. Then you add them together, you get meters squared per second to the fourth, and you take the square root. So the square is, it goes away by a square, and you get meters per second squared. All right, so that's the magnitude. One more thing is to find the,
Is this kind of like what the quizzes are gonna be like? That you're gonna like have like 1A and you're gonna
No,
build
no,
off?
no. I can't do that. I would do that if I could. Canvas doesn't do that.
So it's
But-
like separate questions, like complete. Okay.
But they won't be super involved. It should be fairly straightforward.
Okay. Good.
Yeah. Okay, so how do you find the direction? Was there another question? Someone else? Okay, so how do you find the direction? By direction, I mean angle, right? So in case you... So you got to sketch it out, right? Well, at least you should do that. So it's... I'll do it in green just to mix it up. It's 10 meters per second in the second squared of the negative x direction. And then it's 2 meters, some pi squared per second squared. Anyhow, in the negative y direction, right? So it looks like this. So that's A, right, at 3 seconds. So how do you find this angle? That's the first thing you should do. Yeah, so the units cancel out. So basically it's, well, I shouldn't cancel out the squared here, just the seconds. So really it's 10 meters divided by 2 pi squared, right? That's what we're doing there, right? And that is, what is it? 63.13? Yeah.
Could you replace the y value with 2 pi meters per second squared? Like you're writing it as 2 meters times pi over seconds. Could you like make it like meters over seconds?
Sorry, one more time?
Would it be equivalent to write like 2 pi meters per second squared?
2 pi squared meters per second squared. It's a squared, right? So it's 2, basically, it's like 19.73 meters per second squared.
Yeah. So could you write instead of what you've been writing, could you write 2 pi and then meters per second squared?
But it's 2 pi squared.
So you can't.
No, because there's a square here, right?
Yeah.
So you have to square the pi. Right? Yeah.
Would it be 2 over 10? Where it's just 10?
That's what I
Oh, my bad. Yeah, sorry.
Thank you.
Yeah. Yeah, so it's 2, sorry, pi per second squared. Yes. Yeah. Anyway, but that is 63.13. I just wrote it wrong, right? Okay, so then how do you find the angle from the x-axis? Yep. So it's 243.13 degrees. All right. So does that make sense? So we've gone through position, displacement, average velocity, average acceleration, right? Does everyone understand how you do those things? Okay. So let's go back to the notes. And the next thing we're going to talk about is how you use these things to start to describe what's known as equations of motion. So basically what we're going to do is things backwards to get how things move. So I'll explain what we're doing here. So we have the acceleration vector, right? The instantaneous acceleration vector. It's the derivative of the velocity vector, right? We just went over that. So the derivative of the x component of velocity is the x component of the acceleration. Derivative of the y part of the velocity is the y part of the acceleration. So what you can do is, given the x part of the acceleration and the y part of the acceleration, what you can do is sort of the inverse order operation and figure out what the x part of the velocity is and what the y part of the velocity is, right? So we're basically doing things in backwards. So what we just did is you're given the r as a function of t, right? And we found v, we found a. That's something you can do. The thing that's actually more useful is to do the opposite. Basically, if you know the acceleration, can you find v of t and can you find r of t, right? This is what we're doing. We're doing everything backwards. So how do you do that? To find the x part of the velocity, we know that the x part of the acceleration is the derivative of it, right? So how do you do the opposite thing? Well, it's the integral, correct? So basically, if you integrate both sides over time, that allows you to find the velocity, right? So basically, what we're doing here is we're integrating over time on both sides, and then we're integrating from some initial time, 0, say, at t equals 0, to some arbitrary time. So you start at 0, and then you go to some time that could be arbitrary. And the limits on the left-hand side go from the initial velocity, when t is equal to 0, to the final velocity at t. So this gives you Vx as a function of t. The integral on this side is just Vx of t minus Vx of 0, and this is just the integral on that side. You don't change that, because you don't know what a of xt is. If you know what a of xt is, you can integrate it, but we don't know. It's just a general thing. So then you add Vx0 to both sides, and you get this equation here. So given the acceleration, at least the x part of the acceleration, you can find the x part of the velocity at any moment in time. It's just the initial velocity at t equals 0, where you start, plus the integral from 0 to t ax at t dt, right? Just the x part of the acceleration. Similarly, you can do the same thing for the y direction. It's the same thing, right? Vy is Vy0 plus the integral of the y part of the acceleration over time, right? Okay. So in general, you can come up with this equation here, because if you add these two things up, right? So this gives you the x part of the velocity. This gives you the y part of the velocity, right? So if you add those, if you put those into the velocity equation, remember v is equal to vx x hat plus vy y hat. You put that into the general equation for v, and you get this equation here. That the velocity vector at any moment in time is the initial velocity vector plus the integral of the acceleration vector over time with these vector times. But really, it doesn't really matter here that you understand this. What matters here is that you understand this part, because this is how you actually do it, right? Given an acceleration vector where you know its x component and its y component, this is how you find the y part of the velocity, and this is how you find the x part of the velocity. But I'm just saying you can put it all together into one equation, right, which is this equation here. All right. So we'll do some examples with this. Probably not today, probably tomorrow, but you'll see how it works. Okay, so suppose this integral isn't an integral, right? You're just, the dt is a really short time, but it's not infinitesimal, right? So how you can find the final velocity vector given the initial velocity vector, if delta t is really small, is approximately equal to this thing here. So in other words, what I'm saying is if you take the initial velocity vector, and you know the acceleration vector, and you multiply it by a tiny bit of time, you get the final velocity vector, right? Everyone kind of understand what I'm saying here? Okay. Now suppose the velocity and the acceleration vectors are parallel to one another, right? Acceleration can be in any direction, right? But just suppose they're parallel, right? They're in the same direction. So if they're in the same direction, what happens to v compared to v0 if I'm adding something to the end of it.
It's longer.
Right, it gets longer. Here's the picture, right? Here's v0, and I'm adding a delta t to the end of it. So this gives you the final vector v. It gets longer. So if it gets longer, what happens to the magnitude? What's the magnitude of the velocity? The final velocity compared to... No. So this is the initial velocity vector. This is the final velocity vector.
Right.
What's true about these two magnitudes? This one's bigger than that one, right? So what does it mean? It means it's moving faster, right? So this is another way you can interpret acceleration. So basically what I'm saying here is if the acceleration vector is parallel to the velocity vector, correct? Then the object moves faster in the same direction, right? So this is how you get something to move faster. If you apply acceleration in the same direction as the velocity, the thing moves faster, right? Okay. Suppose A and V are in opposite directions, right? So suppose V is in some direction, A is exactly in the opposite direction, right? So what happens to here is, it's a little bit hard to see. Here's V0, and then you're adding a vector that's opposite of it to it, right? So these vectors are going in this direction, opposite of V0. So when you add those two things together, what do you get? You get this vector here, right? Because you're subtracting things from it. So what is this compared to that? What is the final velocity compared to the initial? Slower, right? So this is another thing you can take from this. If this is only for these cases here, if V and A are completely opposite directions, then the object slows down. This is how you get things to slow down, right? So you have to apply acceleration opposite of its velocity vector. That's how you get things to slow down, right? Does that make sense? Now, what if you have this case here? This is a little bit harder to understand, but suppose A is perpendicular to V, and you're doing a tiny little short time interval. So you're taking A delta t, because this is the equation, right? For finding V, it's this equation here. You're taking A delta t and you're adding it to V0. So A delta t is perpendicular, right, to V. So V0 plus this gives you V. So delta t is really small. What do you think the length of this and the length of this are compared to one another? It's the same. So what does that mean about how fast the object is moving? It's the same. It's moving at the same speed, right? It doesn't change the speed. But what happens to the thing? It changes direction, right? So this is the most general way to interpret acceleration. So basically, there's two extreme cases for acceleration, right? I guess three, right? Either V and A are parallel in the same direction, then you get something to speed up. If V and A are anti-parallel, basically in opposite directions, it slows down. If A is perpendicular to V, then you get it to change direction. You only get direction change, but no change in speed. And then there's the general case where A has a part that's perpendicular to V and a part parallel to V, right? So what do you think would happen for that case, right? So if A isn't completely perpendicular or parallel, what would happen to the velocity?
Going to change speed and direction.
Right, it changes speed and direction. That's the general case, right? Does everyone understand that? I have a demo for that too, but I have to dig it up. So I'll show you tomorrow, right, how that works. Okay, so does that make sense so far? Okay. So then what you can do is go another step, right? So if you know A, you can find V. Now if you know V, you can also find R, right? Which is the position, what the object, where the object is at any moment of time. So the derivative of the basically x component with respect to time is the x part of the velocity, right? The derivative of the y part, or the y coordinate of the object, is the y part of the velocity. So you do the same thing that we did for get from acceleration to velocity. You integrate both sides, right, of this thing here. So Vx is dx dt. So you integrate both sides. I'm going to skip the details. And you integrate from 0 to t again, just like we did for velocity. And what you get is this is x0 is the position, the x coordinate at 0, t equals 0. X of t is the x coordinate t. And that's equal to, the difference of those two things is equal to the integral of Vx over time. But this is the x part of the displacement vector. Remember, a long time ago. Delta r was delta x hat plus delta y hat. So this is the x part of the displacement vector, just the integral of the x part of the velocity. And obviously you can do the same thing with the y part, which I'm skipping down here. The y part of the displacement is just the y part of the velocity vector, right? Integrate. Okay, so there's two ways to look at this. Either you can use this to find the displacement vector itself, which is just delta x, or you can use it to find the x coordinate, the actual position of the particle, x of t, right? So if you add x0 to both sides, this is the position of the object at every moment of time. It's the initial position plus the integral of vx of t over t. And similarly, the y part, the y coordinate is y0 plus the integral of the y part, right, from 0 to 10. All right, so does this make sense so far? Okay, so let's see if I think I have an example here. So basically what we're doing now is things in opposite order. Actually, what I'm going to do is go on to the next thing and do, I'm not going to spend a whole lot of time talking about this actually. The next thing I want to talk about is using what we just learned to talk about, well, that's spelled wrong. So, I don't know, whatever. Okay, so actually go talk about what we just did, what I just talked about, but apply it to basically a simple case of 1D motion. Then we're going to do what we just talked about to 2D motion. So 1D motion is slightly simpler than we've been talking about. So 1D motion is basically just going back and forth, either completely in the x direction or completely in the y direction. So what we just did before was a 2D path where you're moving in the x and y direction. So instead of moving completely, moving in a 2D path, suppose you're just confined to moving back and forth in the x-axis or back and forth in the y-axis, right? This is 1D kinematics. So suppose you're just moving back and forth in the x-axis. You can do the same thing for the y-axis, right? If you're just moving back and forth in the x-axis and you're talking about the displacement vector, right, which we talked about today, the displacement vector is the displacement in the x direction, x hat, plus the displacement in the y direction, y hat. But if your delta y, if you're always at the same y value, what's your delta y? 0, because you don't change y coordinate, right? So no matter where you are on the y-axis, if you're just going back and forth in the x direction, then delta y is equal to 0. So therefore, if you're just talking about 1D kinematics, just things moving back and forth on the x-axis, your delta r is just delta x, x hat, right? There's no y part.
Mm-hmm.
Now, this gets a little bit confusing, but you'll get used to it in a bit. Normally, we write a displacement vector like a vector. What I mean by that is you write it with an arrow over it, right? But because this thing, if you're talking about 1D kinematics, things moving back and forth just in the x direction, it only has an x part to it, right? There's no y part to it, right? It's delta x, x hat. So therefore, you sort of don't need to talk about the x hat because it's implied, right? It's implied that you're going back and forth in the x direction. So we can say that delta r is basically equal to delta x. You don't have to write it as an x hat all the time because it's implied that you're going back and forth in the x-axis, right? Right. So the notation changes slightly, and it will change slightly again, as you'll see. Okay, so how does the velocity and acceleration work in 1D, right? So this is the general equation for velocity. It's the x part of the velocity, x hat, plus y part of velocity, y hat. Same thing for acceleration, x part of the acceleration, x hat plus y part, y hat. But if it's just going back and forth in the x direction, vy is 0 because it's not changing velocity in the y direction. Because the velocity isn't changing, acceleration is 0, right, in the y direction. So it's just vt, v of x, but v at t, right, because all of the velocity is in the x direction, right? So it's just v at t. There's no need for an x here. All the velocity is in the x direction. X hat. So we can write this as v at t, right, instead of writing it as v at t x hat, because it's implied that it's going back and forth in the x direction. And the same thing for acceleration. You can just write it as a to t, right? All right, so there's a slight change in notation here. Okay, so how does the amount of the displacement vector work, right? So the displacement, the amount of it, right, is the x part of the displacement vector squared plus the y part squared. This is the general way of finding the magnitude of the displacement vector. But this is 0, right? So it's the square root of delta x squared, which is what? It's just delta x. It's actually the absolute value of delta x, right? So basically, it's just the absolute value of the displacement is the magnitude of it, is what I'm trying to say, right, in 1D. Okay, so then what we're going to do is, instead of writing it as a vector, something's just moving in the x direction, right? That's all it's doing, it's moving in the x direction. You can just say that v at t, you don't have to write it as a vector. You just say it's v at t, and a at t is just a at t. And a at t can be positive or negative. V at t can be positive or negative. So negative means that it's going in the negative x direction, right? And positive means it's going in the positive x direction, right? Then you don't have to worry about all the rigorous notation of vectors, right, if you're going in 1D, right? Okay, so if you're doing things just in 1D, then what we just talked about, you know, the integration stuff we just talked about becomes this, right? So everything's just in one direction. So instead of writing v of x is equal to v0 x of t plus ax times t, it's just this equation here. V of t is equal to v0 plus, v0 plus ax, v0 plus a at t dt from 0 to t, right? Okay, now what we're going to start talking about is constant acceleration in 1D. Okay, so what does it mean if the acceleration is constant, first of all? Then I'll go through this. So suppose you have a constant acceleration. What does that mean? It means that the acceleration doesn't change. It's always the same value. It doesn't depend on time. So it's always something like 5 meters per second squared. Never changes, right? It's always the same thing. What does that mean about the velocity if the acceleration is constant? It's continuously increasing or decreasing, right? Depending. Remember, this is 1D. So in 1D, either A is in the same direction as V or opposite of V. That's the only two cases. It can't be perpendicular because that's 2D, right? Okay. So either A and V are in the same direction. In this case, it's constantly getting bigger, constantly going faster, right? Or A and V are in opposite directions. In that case, it's constantly slowing down. That's what it means to have a constant acceleration. Now, in real life, a lot of the times accelerations are nearly constant or approximately constant. Like when you hit your gas pedal in your car, for most of the time you're accelerating, it's constant. Not the entire time, but most of the time. So for that case, the equations work out to be much easier than the general case. So if the acceleration is constant, right, what happens to this? You can pull it out, right, because it's constant. It doesn't depend on time. So then it's a pretty easy integral. It's just the integral 0 to t dt. Well, what's that? It's just t, right? So what you get is this equation here. V at t is equal to v0 plus at, right? So this is what's known as the 1D constant acceleration equation for velocity, right? So this tells you if the acceleration is constant, what the velocity is at any moment of time. It's just the initial velocity plus the acceleration times the time at any moment of time, right? If you graph it, what does this look like? So if I graph velocity versus time, what does this equation look like? So you have something plus something times t, right? And if you're graphing it versus time, what is the a? It's first of all, it's a straight line, right? And the a is what? The slope. V0 is the y-intercept. So if a is less than 0, right, meaning it's negative, right? A is negative. It looks like this, right? The slope is negative, right? Because a is negative. If you interpret this graph, right, suppose it starts here. So this is the 0. This is v equals 0, right? So what's it doing here? Is it going in the positive? Is it v greater than 0, less than 0? Greater than 0, right? So it's going in the positive direction, positive x direction, right? But a is in the negative x direction because it's sloping down, right? So what does that mean? It means that it slows down because A and V are in opposite directions, right? And then at this point here, what happens? It stops, right? And then what happens? It becomes negative and starts moving faster and faster in the negative direction, right? So it's something that's starting in the x direction, basically slowing down, stopping, and then going back in the negative x direction, right? This is what's going on here. Now, in this case here, A is greater than 0, right? So that means it slopes up, right? Because the A is the slope, right? So if A is positive, it slopes up. So suppose it starts here. V is negative, right? So what does that mean? It means that V and A are in opposite directions, right? Because V is negative, A is positive, right?
Mm-hmm.
So what happens? It's moving backwards. It's moving this way. But what happens to it?
It's decreasing significantly.
It's slowing down, eventually stopping, right? So it's going like this, and then stopping, and then what happens here?
It's increasing.
It goes faster and faster because V and A are in the same direction, right? So in this case here, it's going to go like this, stop, and then go like that, right? Here's another case. A is equal to 0, right? We know what's going on here. A equals 0. If A equals 0, what happens to the velocity? It's not changing, right? It's constant. So there you just get a constant straight line, right? All right, does everyone understand these simple sort of graphs? Okay. All right, you know what? That's good enough for today. We'll go do more of this. I got to post these notes too later on.
Thank you.
Yep.